Hi everyone. In this video I want to talk to you a little bit about friction and more importantly the coefficient of friction, this mu value that we have here. And what does it arise from, what types do we have, and then some other things that we can do with it. So with that, there's two different types of the coefficient of friction. One is referred to as the static coefficient and the other one is the kinetic coefficient. So over here, oops, that's a little close. I didn't want to do that either. Hold on. There we go. That we have our static friction, and there we have our kinetic friction. And with this, where does friction actually sort of arise from? Well, if you look really closely at the surfaces of any substance, we would think that you'd think that they were smooth, but when you look at them microscopically, they're really not. There's actually all these little bumps and grooves that kind of sit there and interlock between two things. So as you sit there and as they're at rest, they kind of all interlock with each other a little bit, and it's a little bit, you have to kind of get things going. You have to get all of those little bumps and grooves out from each other. So what we find quite often in dealing with static situations is that the applied force, oops, sorry, right here to just get something going is usually larger than the force to keep something going, which we have over here in the kinetic region. But the force of friction ends up being the applied force as long as we're in a situation in which we are at rest. Keep in mind, Newton's laws haven't gone away yet. You need a net force in order to get an object to change its state of motion. And if it's at rest, it'll continue to stay at rest. So if I'm applying 50 newtons worth of force, therefore, and it's not moving, the frictional force must also be 50 newtons. And we can sit there and also solve for the the static coefficient of friction if we simply just take the frictional force and divide by the normal force of the object, which in this particular case happens to be the weight as well. We end up getting 0.5 for the coefficient. Then moving over to the static region, what we see over here is that it only takes 40 newtons worth of force in order to keep it moving at a constant velocity. So therefore, the frictional force must also be 40 newtons. Again, Newton's laws. We're not speeding the object up, we're not slowing it down, we're keeping it at a constant velocity. So therefore, the kinetic coefficient of friction ends up being a little bit less usually. In this particular example, 40 newtons, and we divide by the same weight of the object, that didn't change, and the coefficient ends up being a little bit less in this particular case. This is true of a lot of different things. Like if you're walking along, you kind of want static. You don't want your foot to slide when it strikes the ground. So what this would look like if we were actually to plot out the frictional resistance versus the applied force, if we plotted it out, we'd see that the static friction would sit there and match exactly with the applied force. So quite often questions will sit there and ask, what is the maximum applied force before the object gets going? And it will give you this the static coefficient of friction. What we're looking for is, what is that number right there? What is that maximum value going to end up being? It's not to say that if we sat there and applied 20 newtons worth of force, well, what that would correspond to is 20 newtons worth of friction. But usually questions will sit there and ask, what is the maximum amount of friction that we can apply before it starts to slide? And we're looking for that little peak that's there. But once we get it going, suddenly there is less friction necessary or there's less force necessary to keep it going, so therefore there's less friction. And we see that clearly here in this region right now. So therefore we can then, if the applied force is the same size as the frictional force, there's no acceleration, but we could have the applied force be larger than the friction, in which case the object would be accelerating. So lastly, what I wanted to talk about in this case is another way to look at some of this stuff, which is kind of neat. If we sit there and take an object and place it onto a ramp or something like that, we have to sit there and use a little bit of vector notation here to sit there and begin to break it down, but there's something that's kind of neat that kind of falls out of this. If the object is just staying put, then the friction force up the ramp and the gravitational force down the ramp must be the same. and mg cosine theta is equal to the normal force here. With that, what we end up seeing is if we take the weight of the object, or the normal force, pardon me, mg cosine theta, and we divide it by the frictional force mg sine theta, the coefficient of friction ends up being the sine of theta, mg sine theta divided by mg cosine theta, which just ends up simplifying and being the tangent of theta. So if you can measure the angle of the ramp and take the tangent of that, you end up getting the coefficient of friction. Another way to do this is if you measure the horizontal distance and that the object for the ramp, pardon me, and then measure the vertical distance the ramp is up, that also does create an angle as well, and that's also the opposite side over here, V, and the adjacent side, H. That is also the tangent of theta, but you just take the vertical height divided by the horizontal height, and that would also give you the coefficient of friction. So that's kind of a neat little trick that you can pull sometimes with this. Anyway, I hope this was helpful and useful. See you next time.